Welcome to today's paper reading. Today's paper is titled, Transformers Meet Neural Algorithmic Reasoners. This paper was published on the AR14 preprint by Wilfried Bounsi and colleagues from Google DeepMind. The abstract highlights the limitations of transformers in handling precise algorithmic reasoning tasks, despite their strong performance in natural language understanding. To address this, the authors propose a novel hybrid architecture that combines the language understanding capabilities of transformers with the robustness of graph neural networks for neural algorithmic reasoners. This approach involves a two-phase training process that allows the language model tokens to interact with the node embeddings from the neural algorithmic reasoner. The effectiveness of this trans-NAR model is demonstrated through significant improvements on the CLRS text benchmark, outperforming traditional transformer models in both in-distribution and out-of-distribution algorithmic reasoning tasks. The introduction of this paper highlights the effectiveness of graph neural networks, GNNs, in solving algorithmic tasks, even on inputs significantly larger than those used in training. However, these systems require structured input formats, limiting their application to more complex, noisy data like natural language. On the other hand, transformers are the current state-of-the-art for modeling noisy text data but struggle with algorithmic tasks, especially when generalizing out of distribution. This paper proposes the trans-NAR model, which combines the strengths of transformers and neural algorithmic reasoners, NARs, to improve reasoning capabilities, particularly in out-of-distribution scenarios. The model is evaluated on the CLRS text benchmark, showing significant improvements. Figure 1 illustrates the trans-NAR architecture, which synergizes transformers and neural algorithmic reasoners, NARs, to enhance out-of-distribution reasoning across various algorithmic tasks in CLRS text. The x-axis represents one of the 8 algorithmic families from CLRS 30, while the y-axis measures average execution accuracy on out-of-distribution examples. This architecture demonstrates over 20% absolute improvement in accuracy for several algorithm classes, showcasing its emerging capabilities in handling out-of-distribution scenarios. Figure 2 provides a high-level overview of trans-NAR, a system that enhances large language models, LLMs, with algorithmic reasoning capabilities. The LLM processes input tokens and generates output tokens, typical of unimodal transformers. The Neural Algorithmic Reasoner, NAR, module, a pre-trained graph neural network, GNN, executes various algorithmic computations on graph-based inputs. During its forward pass, the transformer can access the embeddings computed by the NAR through cross-attention, facilitated by learnable glue weights. In the realm of neural algorithmic reasoning, NAR, recent advancements have shown that NARs can execute multiple algorithms simultaneously and be deployed in various downstream tasks. Our work is influenced by the scalability demonstrated by Nemoroso et al., suggesting NARs can handle significantly larger systems than their training distribution. Regarding length generalization in large language models, LLMs face challenges due to their autoregressive nature. Efforts to improve length generalization include prompting techniques and randomized positional encoding. Our approach focuses on robustness with respect to prompt quality. Lastly, tool use and multimodality offer another path to robust generalization. We view the pre-trained NAR as an internal tool, facilitating communication between the transformer and NAR through embeddings, inspired by multimodal LLMs and cross-attention mechanisms. Figure 3 illustrates the trans-NAR hybrid architecture, which integrates transformer layers with gated cross-attention mechanisms to facilitate information flow from a neural algorithmic reasoner, NAR, to the transformer. This setup generates queries from token inputs and derives keys and values from the nodes and edges of a graph representation of the reasoning task. Notably, when employing pre-trained transformers, the cross-attention gate is initially closed to safeguard the language model's inherent knowledge during the early stages of training. The trans-NAR architecture accepts a dual input consisting of a textual algorithmic problem specification and its corresponding graph representation. The forward pass begins by initializing the inputs, followed by the transformer computing the next step's representation and the NAR processing the graph representations. Cross-attention mechanisms then condition the transformer's token embeddings using the graph's node embeddings to produce the final output. This process repeats until the final layer, where a prediction head converts the output into token logits for the next token prediction objective. The experiments utilize a decoder-only, 6-layer transformer model from the chinchilla family, with 70 million parameters and a context size of 2048. 2 variants are tested, one with pre-trained weights and another with random initialization. Randomized positional encoding is employed to enhance the robustness of reasoning, as highlighted in previous studies. The NAR is pre-trained on the CLRS-30 benchmark, and the experiments are conducted using the CLRS text dataset. Evaluation metrics include the shape score, parse score, and CLRS score, which measure the correctness and complexity of the model's outputs. Table 1 presents samples from the CLRS text benchmark for various algorithmic tasks at a problem size of 4. The table clearly specifies the input and target parts of the examples. It is noted that at this size, variability is limited, leading to trivial answers for some algorithms. This effect is expected to diminish as the problem size scales. Figure 4 illustrates the superior performance of TransNAR over the baseline transformer across various algorithmic tasks and input sizes. The largest in distribution size tested is 12, with 10 and 14 being out of distribution, testing interpolation and extrapolation respectively. The y-axis range for in-distribution settings is adjusted to 0.7, 1.0 due to transformer's easier generalization. The TransNAR consistently outperforms the transformer, evident in both initial training and fine-tuning phases. The CLRS score is used as the evaluation metric, with each model trained using 4 random seeds, and error bars indicating plus or minus 1 standard deviation. Figure 5 highlights the superior performance of the TransNAR model over the baseline transformer in producing outputs with correct shapes. This metric reveals a significant weakness of standard transformers when dealing with out-of-distribution data, their inability to correctly manage the relationship between input and output sizes. The TransNAR model significantly mitigates this issue, demonstrating numerous improvements. However, these enhancements do not always result in perfect scores, suggesting that further research in this area could yield even greater benefits. The authors presented a hybrid architecture that integrates the language understanding capabilities of a transformer with the robust algorithmic reasoning of a pre-trained graph neural network. This model demonstrated superior performance compared to a transformer-only model on the CLRS text benchmark, particularly in out-of-distribution scenarios. The authors suggest that future research should focus on datasets with ambiguous problem specifications, which are more representative of real-world challenges, and where symbolic inputs are not provided in advance. Thank you for watching.